from Lawrence Livermore National Lab, and she will tell us about nuclear reactions from first principles.
Hello, and good evening or good morning, everybody, depending where you are. Yes, so as Hans just mentioned, I've been asked to give a little bit of I guess, an overview about how we can compute nuclear reactions from first principles. So to start with, of course, I'm going to just remind you that reactions among like nuclei play an important role in understanding the origin and evolution of our universe. And, you know, starting all the way from the Big Bang to solar fusion cross-sections and going all the way to helium burning, or, you know, even reactions that are important for terrestrial applications, like, for example, terrestrial fusion. And then, of course, you also know very well that because these are reactions between positively charged colliding nuclei that repel each other, the fusion process operates mainly through by tunneling through the Coulomb barrier, and therefore the cross-section drops nearly exponentially with decreasing energy. And in fact, typically, rather than the nuclear cross-section, we are interested in looking at the astrophysical S factor, which is the nuclear contribution of the cross-section once we remove the tunneling through the Coulomb barrier. And because cross-sections drop nearly exponentially with energy, what happens is that typically they are quite difficult, if not sometimes impossible, to measure at the very low energies we are interested in when it comes to the environment of stars. So, for example, here I'm just picking one of the possible examples, a solar fusion cross-section, specifically the beryllium-7 P gamma cross-section that produces boronate, and then from the decay of boronate produces the high energy neutrinos that we can detect here on Earth. So as you can see, this S factor has not been measured down to the very low solar energy we would like it at, and basically we need to resort to theory in order to extrapolate it down to the to zero energy, and then these of course introduces uncertainties. And it is really our goal to try and arrive at the as accurate as possible evaluation of these reactions at astrophysical energies. So because of these, ideally we would like to really develop a predictive theory of nuclear reactions that we can trust and can give us accurate evaluations. And currently, the best path that we have to get such a predictive theory consists in combining effective field theories of quantum chromodynamics, and in particular chiral effective field theory that help us organize the nuclear force into systematically improvable expansions with ab initio methods. And in particular, for if you're interested in describing nuclear reaction, we really need ab initio many-body methods that provide a unified description of both the structure and the reactions of nuclei. And of course, this is a very computationally intensive field. Okay, so I should mention that, of course, when it comes to few nucleon systems, there are, so from 2 to 4 nucleon systems, there are several very accurate, if not numerically precise, I wanted to say numerically exact methods to describe both the structure and the reactions of nuclei. And but the issue starts to become more complicated when we are trying to describe reactions in p-shaped nuclei, and it gets, of course, more and more difficult as we move towards medium mass nuclei and heavier nuclei. So, but okay, I wanted to discuss some at first some general principles that can help us to arrive at such an ab initio description of nuclear reactions. And in particular, there is a framework that it is really useful to bridge ab initio many-body theory and collision theory, and that's the R-matrix theory. So R-matrix theory and R-matrix principle relies on a division of the configuration space into an internal and external region. And at the boundary of the region, is delimited by a radius that is typically called the channel radius. And this channel radius can be chosen large enough so that in the external region, the system interacts basically only through long-range interaction, therefore just the Coulomb interaction. And instead, in the internal region, the system is still experiencing, the two nuclei that are reacting are still experiencing the nuclear interaction among them. So what we do in our matrix theory is that in the external region, we approximate basically the scattering wave function using the asymptotic solution of the problem that are known, so basically Coulomb wave functions, while the internal region is considered finite, and we can use I am getting ahead of myself. Apologies. So we in the internal region we need to parameterize the solutions of the system, and if we can match the solutions at the channel radius, from it we can extract the elements of the scattering matrix, and from it compute the cross sections. And the most familiar ways the R-matrix theory is utilized typically as is phenomenological R-matrix, where the internal region is parameterized with the pole expansion of the R-matrix, and then the parameters are fitted to the experimental cross-section data, and one repeats, one basically tries a set of parameters, goes through the calculation of the various observables, and then starts repeating until a fit is reached. But there is no real need to, we are not confined to use the R-matrix in this phenomenological setting. We actually can use a microscopic R-matrix theory. Basically, if we are able to provide, to describe the interactions in the internal region for a microscopic theory of nuclear forces and nuclear structure, then we can use the same setting. So as I was saying, the internal region is considered as confined, and therefore we can use an expansion. And in particular, we can use, for example, what is called the resonating group method expansion. Another thing that I want to point out is that on top of this framework, on top of allowing us to compute scattering matrix and cross-section, allows us also to compute bound states, because from the matching of the internal and external region, one can also extract asymptotic normalization constants and the corresponding binding energies, and therefore one can then use the solutions to compute bound state properties. Okay, so the starting point of the resonating group method is the usual translational invariant microscopic nuclear Hamiltonian of the A-nucleon system. Except that rather than using the this usual form we're all used to see, it's better to just rewrite it in terms of by isolating the components that pertain to the target. So the target Hamiltonian, which comes with its own eigenstate, the projectile Hamiltonian with its eigenstates, and then we have, of course, the relative motion Hamiltonian, so the relative kinetic energy, the average Coulomb interaction between the nuclei, and in addition to it, of course, we also have in the internal region, we also have the intercluster interaction between the projectile and the target. And I am underlining here that this intercluster potential only if the channel radius is chosen large enough, this intercluster potential only exists in the internal region, and in particular also if one consider if this interaction contains the point Coulomb interaction, the subtraction of the average Coulomb renders it a localized potential as well. So, okay. So now, if we now consider a model in which we have a target and a projectile, here I'm making an example in which the projectile has 3 nucleons and the target has 4 nucleons. And we consider a model in which the wave function of the projectile and the targets are obtained within the ab initio no-quotient model. Then one arrives at the no-quotient model combined with the resonating group method. And what I mean by saying that the target is the no-quotient model eigenstate is that we are using an expansion in many body harmonic oscillator basis states of this type. But what I want to underline, and so these are, in general, these are translational invariant coordinates, so they will depend on the Jacobi coordinates of the target projectile. And I want to underline that these expansions contain all excitations of the nucleons from the ground state configuration up to a maximum excitation of an Nmax quanta that is chosen in the calculations, and we use consistent values of the excitation for both the target and the projectile. Now, using this no-quotient model eigenstates of the target and the projectile, then we can assemble, we can build what one calls coordinate space channel bases that basically are simply coupling these eigenstates, to a spin channel, and then we couple them to angular momentum, and we can use now these channel bases as a basis to represent the projectile target wave function in the internal region. So basically, we use expansions of this kind. However, one has to make sure to anti-symmetrize these channel bases that I have shown here for exchanges of the nucleons across the 2 clusters, which are not taken into account yet in the formalism. So this has to be done explicitly. Well, using these ansatz, of course, then the Schrödinger equation in this model space becomes a set of integral differential equations for the relative motion amplitudes that are the unknown that are left to determine. And these are the no-quotient model RGM equations. What we see here is the Hamiltonian kernel, which is basically given by the matrix element of the intrinsic Hamiltonian on this anti-symmetrized channel basis. And we also have a norm kernel because this type of basis is not orthogonal, is overcomplete in general, but this is not a major issue. It can be dealt with easily. Okay, so if we then use these solutions in the internal region, then we can use our matrix theory to match in the external region and find scattering wave function, bound states, and all we need to go ahead. Now, the most computationally intensive part of this approach, of course, is to compute the integration kernels. And what makes it especially difficult is that, as I mentioned, we need to account explicitly for these anti-symmetrization operators. So it turns out that to compute these translational and invariant integration kernels, it's rather than working in a Jacobi coordinate, as invariant coordinate I showed earlier, it's actually more efficient to work with a single particle basis and specifically with the configuration of this kind, when we have a target with a 0 center of mass motion, and then we have a projectile which instead has an excited center of mass motion. And one can prove that working with the harmonic oscillator Faddeev states, one can transform exactly from this configuration to the desired one, that is the relative coordinate one. And so one can exactly remove any spurious center of mass motion that is introduced by working with this basis. And I have briefly denoted the C here, what I was calling before the channel basis. So now if we work with this type of single particle wave functions, in the past, what we have done is that we have used no-kosher model solutions in second quantization representation, so Slater determinants, to represent the target with this 0 motion of the center of mass. But we continue to represent the projectile as a Jacobi relative coordinate states, and then we're adding these additional motion of the center of mass coordinate in an excited harmonic oscillator state. And this was useful. However, there were a few drawbacks. These continued to require explicit antisymmetrization of the channel wave function. And what that meant was that the formalism was dependent on the number of nucleons in the projectile. So it was specialized to the projectile that was used. Although it had the benefit to be general with respect to the total number of nucleons. And so this formalism was extremely successful actually, and has allowed us to perform a calculation up to the nucleon projectiles, but it became quite expensive, or less convenient to use once we wanted to go beyond nucleon projectiles. But recently, and this is work that was done by Kostas Karvaris, who will talk after me, we introduced a new way of building these single particle channel states, in which basically we use Slater determinants to represent both the target in its 0 center of motion and the projectile with an excited center of mass motion. And this is done by basically starting from the Slater determinant of the projectile, the eigenstate obtained with a no-kosher model, and then boosting the center of mass of the system to a higher excitation through the required operators. So what this means is that the channel state can be represented as the sum of Slater determinants. And so this means that we don't need any longer to explicitly antisymmetrize. Everything is taken care of easily. And this means that one can start using this approach to do reactions with alpha particles and even p-shell projectiles. Okay, so of course, the resonating group method has its limitations, and a special one is that it has difficulties in in accounting for the excitations of the core, and if you want, the internal excitations of the projectile and target during the reactions. And to show this, I am showing the example of neutron alpha scattering in this plot, in the scattering phase shift. And what I'm showing here are calculations in which these core excitations, we try to represent them by including as many as we can excited states of the helium-4 target. And what you see here is a sort of convergence with respect to the number of the excited states that are included. And it is apparent that it is fairly slow, and up to 7 eigenstates have been included, and one can start asking have we really reached convergence? The answer is not completely clear. It would seem so, but for the P1F case, it's not entirely clear, for example. And so ideally, we want to try and solve this issue. Well, the solution is that one has to go beyond the resonating group method ansatz, and one has to consider a generalized cluster expansion. And in particular, what we do is consider an expansion in which we have now two set of basis states. One is a set of localized A-nucleon solutions that are eigenstates of the intrinsic A-nucleon Hamiltonian computed within the Nocosher model. And then we have, as before, an expansion in continuous microscopic cluster states that are obtained within the Nocosher model resonating group method. Now, this generalized cluster expansion has the advantage that the Nocosher model eigenstates describe efficiently the situation when all nucleons are close together and the short range many body correlations of the systems. And instead, the resonating group method basis states describe efficiently when the reactants are apart, and then describe well clustering and correlations within the system. So this is what we call the Nocosher model we continue. And besides being useful for describing reactions, this approach is also very useful to describe clustering halonuclei, and really one can describe bound scattering states and resonances all on the same footing. The Nocosher model continuum has a set of equations that are an extension of the Nocosher model RGM equations. It's in this case we have both discrete and continuous amplitudes to solve for, but basically these are the kernels that I showed earlier. But then we have also the Nocosher model component of the kernel for the Hamiltonian. These are just energy eigenvalues, and then we have the coupling coming from the matrix element, in which on one side we have RGM states, on the other side we have Nocosher model states. Once again, these equations can be solved using microscopic matrix theory, and one can then find scattering matrix or asymptotic normalization coefficients. So going back to the example that I gave earlier, now if we work within the Nocosher model continuum, we have no problem to take into account all the core excitations, and that's because the eigenstates of the aggregate nucleus, that in this case was EM5, compensate for the missing core excitations that we were not able to include in this case EM4 excitations. So you can see again the convergence that I showed earlier, but in this case it's really clear that there is no dependence. And so of course this makes life much easier. And this was a very nice work that was done by Guillaume back in the days when he was in Livermore. Okay, so just to give you an idea, the approach works. Recently, not so long ago at least, there was also a benchmark calculation done with the new 5-body Faddeev-Yacubovsky calculations from Lazauskas for a nucleon potential, I believe it was in 3LO potential. Which shows that the two calculations agree very well. And now with this method, we can use chiral nucleon forces and predict reactions ranging from elastic scattering, for example, this is proton elastic scattering of helium-4, to more complex transfer reactions. What I'm showing here is the deuterium-tritium fusion, and what I want to, in which the initial and final channels of the reaction are actually two different channels. So this is computationally, this was a massive enterprise, massive calculations that Guillaume once again took when he was in Livermore. what I want to highlight here is that the Nokoshimodel continuum calculation, starting from chiral interaction, actually produced this dashed green curve initially, and the difference with respect to the experimental data is basically given by just a 5 kiloelectron volt correction on the position of the resonance position for the 3/2 plus resonance, which is, some kind of fine tuning that can be really, really hard to get if one is doing calculations from scratch, right? But what can be done in the Nokoshimodel continuum is that one can actually use the Nokoshimodel eigenvalues of the Nokoshimodel part of the basis. They can be used as adjustable parameters. So, for example, in the case of the deuterium-tritium fusion, a single 3/2 plus eigenvalue was used as the adjustable parameter in order to produce the required 5 kiloelectron volt correction of the resulting 3/2 plus resonance, and everything else was still coming from prediction. All other characteristics of the scattering matrix and everything else was width, etc., were still continued to be predicted from the initio method. And so this is how we obtained now the very nice agreement with experimental data. And after that, we could use our method to predict actually the polarized neutron-tritium fusion, for which there are actually no experimental data. And so this is really a prediction. But so the approach, as I mentioned earlier, can also provide a description of clustering and specifically of halonuclei, and also, more importantly, a unified description of the structure and the reaction of halonuclei. And as an example here, I have the study of barium-11 that was done by Angelo Calci back in 2016, I think. And what I'm showing here is a study of how the spectrum of energy levels of barium-11 varies, or depends on the type of trinucleon force that is included in the calculation. And here, what we did was to play a little bit with the regulator of the trinucleon force to see what effect it had. And then we also performed calculation with the N2LO-SAT chiral interaction. And what is shown here is that, of course, as usual, when we are just using the two nucleon part of the interaction, it was the chiral and trilow potential, we cannot obtain the parity inversion of the grounded first excited state of barium-11. And then by reducing the cutoff in the regulator of the trinucleon force, it looked like we were, reaching the inversion, but it didn't really, things didn't really work out because when we are, using, if the regulator is too small, we go back basically to the situation of the nucleon interaction. But then with the N2LO-SAT interaction, we find, even though barely, if you want, the required inversion of the two bound states. And so once again, so we find the correct ordering, and once again we can use then a little bit of phenomenology to actually get the phenomenological binding energy of barium-11. And what is shown here are the Nokoshimodel continuum, the components of the Nokoshimodel continuum wave function for the barium-11 ground state, and in particular for the S wave here, the dashed line is the original result, and the solid line is the result obtained after a little tuning of the Nokoshimodel eigenvalue. So it's really a minimal change, but then it gives us the correct description of the binding energy. And so after this tuning, then we can go ahead and compute, for example, the photodisintegration cross-section of beryllium-11, and these are our results. And you can see how that we then obtain the better, we obtain agreement with here with the Riken results, while there is this discrepancy between Riken and GSI results. Our curves agreed better with the Riken data. But perhaps more interestingly, as Chloe has already mentioned yesterday, one can use the asymptotic normalization coefficients obtained from an Okoshar model to inform a halo EFT theory, and then the description of direct reactions of beryllium-11 on heavier nuclei. So I see that I'm running out of time, perhaps. So I will just be quick, and we are just say that we are now applying this framework to predict this, solar physical section and the beryllium-7 P gamma cross section that I mentioned at the beginning. Here are some preliminary results that are looking, very promising. And we are also, this is a work that Kostas Karvaris is doing, and we are also predicting cross sections for Big Bang nucleosynthesis. These are preliminary results obtained by Chloe Hepburn for the alpha D capture on lithium-6. Once again, very promising, but still a lot of work ahead. And just really for information only, these formalisms, the Okoshar model RGM and Okoshar model continuum formalisms, can be extended to the description of three cluster dynamics, and one can also apply them to address many body correlations and three cluster dynamics in Borromean system, for example, in 6, both for the bound states and continuums. And so I've come to my conclusion that we do have an efficient termination approach to enable a unified description of structure and reactions, at least in light nuclei. And in this calculation, actually, so these unified structure and reaction calculations, ab initio calculations, are actually interesting because they can be used to inform halo EFT and then few body models of direct reactions. And then, of course, we are interested in arriving at accurate predictions for Big Bang and solar fusion cross sections, and also helium burning cross sections. I didn't talk explicitly about it, but I want to make sure to stress that there is also progress on other fronts. There are Green's functional Monte Carlo calculation of reactions, nuclear lattice effective field theory combined with the adiabatic projection method that has done alpha-alpha scattering, and of course there are a lot of developments in the area of microscopic optical nucleus potentials, and with this I'm done. Thank you.
So thank you, Sophia, for this very impressive overview. We have some time for questions. Daniel?
Sophia, I agree with Hans. This is a really impressive overview. So as you might guess, I'm particularly interested in the connection to halo effective field theory. So it's possible that what I'm about to ask is a question that we should defer until after Kostas's talk. But if I look at your beryllium-7 P gamma results, I think it's fair to say that studies in cluster models and halo EFT tell us that the very low energy cross-section here is completely dominated by the ANCs. So I was wondering if you could comment on what you get for the ANCs, because as Chloe emphasized, right, I think that's a great meeting ground for. So
actually, that's exactly something that Chloe has been summoned on. I think about yesterday we were discussing it. We have now a bunch of results also with other chiral interactions, and we want to analyze these results in more detail. So they're very fresh. We want to analyze them in more detail. We want to look at the ANCs. We want to look at the scattering length that we get, and provide this type of answers. I don't know if if Costas off the top of his head remembers any ANCs. I kind of doubt it right now. I'm putting him on the spot, but
I absolutely do not.
there you go. That we can
I
give.
mean, I don't remember what the quote unquote right answer is, i.e. what the answer that you get if you fit the data.
But we
right?
definitely want to get those and and analyze what the situation is. We agree with you, definitely.
Yeah, I mean, yeah, I think so. Certainly, the halo EFT calculations suggest that the cross section up to 500 keV is describable in terms of a fairly small number of low energy parameters, and so if you get those right, you get that right. Yeah.
And I don't know if Chloe has anything to add to this, perhaps.
No, I agree with you both. I think that we should analyze what the influence of the ANC on this low energy part of the S factor.
Yeah.
But yeah, this should be done, will be done.
Cool, thank you.
Okay, further questions? Grigory?
Thank you, Sophia. Wonderful talk. You have this peak here at 2.3 MeV. Seem to disagree with the experimental data. What is this feature?
Well, the peak, so this figure does not show it because it cuts a little bit too early in energy, but there is actually, maybe you can start to see it. There is a little bump here in the experimental data. So there is a resonance, a broad resonance there too. The problem is that with this interaction, it's a little bit too quote unquote overbound. So it comes at the lower energy. And so this is one of those features, or if you want fine tunings, that one can correct a little bit by tuning one of the parameters of one of the eigenenergies of the Nokoshan model. We continue.
Do you remember what state is that? Is it the 3+?
Can you help me here, Costas, perhaps? I think it was.
Yeah, I was going to say that to add to this a bit, the other problem is that the data there are from Coulomb dissociation, I think. So the bump is in E2, but the points mainly pro B1 transitions. So you have that thing as well. The bump is further up.
Oh, can I also comment here? So this is the 3+.
Yeah,
so this is in the right position. But as Kostas says, I mean, these are the data are from the breakup, so they are not sensitive to the M1 or E2.
Thank you, Peter.
Hi, Peter, I had not realized you were on the line.
Okay, so thank you. I think in the light of time, we should continue with the next talk. We have more time for discussion at the end. And the next speaker is Konstantinos Kravaris, and he'll tell us about ab initio clustering in beryllium-12. So please.
So hello, can you see my screen just fine? Okay. So hello, thank you to the organizers, first things first, for making this happen. I understand that everyone's time is a precious commodity these days, so I'm really thankful for their efforts. There's been a great workshop. So the announced title was ab initio clustering in 12 beryllium. However, based on the discussions and the rest of the workshop, I figured I may take a little slight detour in the beginning to go on and motivate the talk in a little bit different way than usually. So if I manage to change slides, cool. So the diagram on the left, I think we've seen to death at this point. So we know the basic premise here. You have a parent nucleus and you expect it to cluster into a daughter nucleus. Well, let me change this into a laser pointer. You expect it to cluster into a daughter nucleus plus a cluster near threshold. How this is seen across many like nuclei, and we are content that this works. However, that's not the whole story generally. So we know there are other broad resonances across multiple light nuclei. We have all these 0+ states, for example, these 2+ states that saturate a lot of the alpha with even much higher energy than the threshold. These states are very broad, so we expect them to have definitely clustered characteristics, so they will look like an alpha plus daughter nucleus. And it is really, at least to me, a question of how do these states survive all the way up in that high excitation energy? How do you still get an alpha cluster when you can decay in so many different ways everywhere, and how the strength is collected in just one state completely? Okay, so experimentally, people have studied alpha clustered states for many, many years, as you can see from the oldness of this graph. And one very straightforward way to do this is to do alpha transfer reactions. So if you want to study alpha clustered states in 20 neon, you can take a 16 oxygen target, 6 lithium projectile, and then essentially drop an alpha particle in the 16 oxygen. So this preferentially will create states that are natural parity, as you can see here, and it is bound to create states that definitely look like an alpha plus a 16 oxygen. So out of about, I don't know, 60 states in 20 neon, you only see a handful here, right? So this is a testament really to the selectivity of the alpha transfer reaction. These resonances, the alpha structure content can be probed in traditional structure approaches using spectroscopic factors. So what I'm showing here is the alpha spectroscopic factor for each of these peaked, well, which peaks at exactly the same resonances that we see here. Granted, there are more, but these are sort of at higher energy, so there are issues with the calculation. This is a 0+1 particle hole excitation shell model calculation. So nevertheless, we do get this collective effect in the shell model. This is traditional shell model, by the way, not no-core shell model, I should say that. So yeah, you get high spectroscopic factors for the states that are preferentially populated, so you can be content that you're essentially reproducing what you see in experiment. The problem, however, with spectroscopic factors is that they're not really observables. And so comparing directly with experiment is a bit of an issue. And to make matters worse, how you define spectroscopic factors is a little bit quirky at best. So here, what I'm showing is data for, again, alpha spectroscopic factors for ground state to ground state transitions across the SD shell. And the points are alpha, either P alpha P or 6 lithium D reactions. And okay, of course they are scattered. And this again is a testament to the problem that spectroscopic factors are not really well defined. So when you extract them, they are really model dependent. But you see a general trend, right? You start off somewhere here, and then you go down, but then eventually, once the shell is full, you now have high spectroscopic factors again. That is not the case for the theoretical prediction if you use the traditional version of the spectroscopic factor. So what you get is spectroscopic factors that are small and just keep getting smaller and smaller as you increase the mass of the system. However, if you use the Fleischbach spectroscopic factor, which is essentially renormalized across the channels, takes into account the non-orthogonality of the decay channels, I should say, you do start to get a better reproduction of experiments. So you do still reproduce this high spectroscopic factor, at calcium 40, you do get the dip, so everything seems to be working. But again, this is a problem, right? If you want to be predictive, you should have something that you should be looking at observables and quantities that you can actually compare to experiment. And we really do want to be predictive if we want to look, for example, at the alpha burning process, because this is just a series of cluster enhanced reactions, right? You have beryllium made ground state, which is essentially the best cluster place ever. And then you add another alpha particle, which is enhanced by the Hoyle state, which is also cluster. So we know the cluster state will enhance reaction rates in this case, or will facilitate is probably a better word. So we want to be able to see how clustering emerges and how it helps in these reactions. And furthermore, as Sophia mentioned, we want to be predictive so that we can extract S factors at low energies, because at the end of the day, experiments can only go so far. As you go to lower and lower energies, things are suppressed. And to make matters worse, it's not only that you have less data points, it's that you have larger error bars. So when you try to constrain any phenomenological model, using error bars that are just so huge, it's not really adding a lot to it. Nevertheless, that's not, at least for me, it's not the only thing, right? You don't just want to fit to experiment and get an extrapolation to low energy. You want to understand how the many-body complexity assists in getting this specific cross-section. What are the important ingredients of the nuclear force that give us these specific reaction rates and make up the carbon-oxygen, for example, ratio in the universe? So, okay, so in order to tackle these questions, we use ab initio microscopic approaches. I think Sophia definitely described all of this very, very well, so I'm not going to bore you with the details. We use the no-core shell model with continuum. So the first reaction we would like to tackle is the alpha-alpha reaction, right? Because it's the first reaction in that alpha burning cycle. Now, at this point, we still don't include the core polarization effects for the projectile and target. So this is purely a no-core shell model with RGM. So it's two alpha particles described in the no-core shell model and then being scattered using the resonating group method. What is shown here is the alpha-alpha scattering phase shifts. And the dot-dashed line that you see in the middle is the result that you get if you use only the nucleon-nucleon part of the interaction. The dashed line and the red line correspond to calculations that include the same three nucleon force, however, regulated in a different manner. So in one case here, we have a local regulator, and the solid line has both a local and a non-local, non-local regulator. And this goes to show how really the fine effects of the nuclear interaction are what will give you correct reproduction of the thresholds, or they will give you a good position of resonance. Because when you include only the local regulator, you get overbinding. And this is overbinding by about 1 MeV in the resonance. On the other hand, if you use a local, non-local, you get less binding. So things tend to be pushed further apart. And this is in agreement, I think, with what Dean mentioned earlier in the workshop. Again, if you look at differential cross sections, you see exactly the same effect, obviously. But in order to get good agreement with the data, it now becomes very crucial to know exactly what's in the interaction that you're feeding. Moving on, the main topic, I guess, of the talk is clustering in beryllium-12. I personally like beryllium-12 because it has multiple modes of clusterization one could have. So you could think of it as 6 helium plus 6 helium. You could think of it as alpha plus 8 helium, or you can think of it in any mixed mode that has 2 alpha centers, and then the neutrons are sort of spread out. And the question, the graph that sparked my interest, I should say, is basically this experiment from 1999, where you see this nice close J = 6 resonance structure. So in order to have two states with similar, well, the same spin and parity, but in this case, you do not see parity, it means that you have two fundamentally different structures within them. So they have to be somehow different. Otherwise, they would be much further spaced apart. And this is something that I really wanted to see is, can we reproduce it from within a microscopic model? Can we reproduce it from the no-core shell model? Okay, and as a side effect, it's a nice testing ground to see how does opening structure models to the continuum will affect reaction observables, right? So it's easy to make a simple RGM calculation and not connect it to the continuum and just have the cluster modes interact with themselves and see how they lay up in the spectrum. But then it's a question, okay, now you added the continuum, now you've added all this place for the strength to go. So where, how does this affect your final result? So to start, we do a calculation containing only 6 helium plus 6 helium clusterizations. We get a nice rotational band and then a couple of other states. Note that these guys here are bound because we do not care about the 11 beryllium plus neutron threshold yet. So this has not been included in the calculation, so they don't have any decay width. Then, oh, sorry, we can do a calculation for alpha plus 8 helium. Again, the threshold of importance is here. This contains only 4 helium plus 8 helium, so you still have 0, 2, 4, 6. Now you have a negative parity band because you're no longer dealing with identical object scattering. But you see already this 2, 6 pluses in relatively close distance. I should say at this point that this calculation only uses the nucleon-nucleon interaction, so it's not the reproduction of experiment when it comes to specific energy level positions is not perfect by any means. Okay, so now we can make a calculation that includes both cluster configurations. So essentially we can turn on the interaction between these cluster configurations. And what you observe is the typical 2-level system behavior. The 0 plus from here and here interact, so they spread further apart. The same for the 6 pluses and the 4 pluses and so on. The 4 plus is not so much, but still just a little bit, which is a little bit interesting in and of itself, but it requires a little bit further investigation there. However, the spectrum becomes really nice when we include the 11 beryllium plus neutron clusterization. So again, you'll notice that the ground state is overbound. However, we do still have a spectrum. We now have unnatural parity states, finally, because 11 beryllium plus neutron can allow us to have that. But generally, you see a little difference in the higher spectrum. That being said, there are a couple of guys that require noticing, and one is this 0 plus, so it doesn't really move relative to the threshold. However, it now obtains a very narrow decay width. However, the most important thing to note here is the 2 plus. So this 2 plus was very narrow in the calculation, including only the cluster modes. However, it was there, so we know it has to be a cluster state in these calculations, at least of some mixed clusterization. However, when you turn on the 11 beryllium plus neutron channel, it becomes surprisingly broad. And it becomes surprisingly broad, not in general, it's not only the total width, it's also the widths that are probed with reactions that are meant to sort of investigate what the cluster widths are. So the 6 helium plus 6 helium, 6 helium alpha 8 helium reaction, we see that this broadness in the state is very clearly visible. So it's just by including the neutron in the calculation, we see that it has a severe effect in the cross section that we measure. Finally, there is this 0 minus who was first observed in March. It's really exciting to see it pop out of the ab initio calculation all by itself. Didn't have to do anything there. Finally, do I still have time? Sorry, I forgot to.
Yes, you have 5 more minutes.
Okay, cool, great. Finally, we can now also start looking for other places where we could hopefully see cluster effects. And one of those systems is 7 lithium. It's not a system that would pop out if you were thinking clustering. However, what you have is these 2 5 minus states right here, which are just, and you have the 6 lithium plus neutron threshold right in the middle. So the alpha T threshold is already open. So now we have 2 states, we have 2 possible cluster modes, and they are in very close proximity. So this is the cluster mode coexistence that I mentioned before. And in fact, you can actually take the resonating Noether shell model with continuum and then start adding extra factors that increase the mixing between these states. So what is shown here is 2 different calculations for the elastic and the transfer 6 lithium plus N reaction, so 6 lithium NT and 6 lithium elastic. And you see how much the cross section changes when you just increase or decrease the mixing. So the small calculation has smaller mixing, this has bigger mix, the dashed calculation has bigger mixing. So essentially you have, if you want to reproduce experimental data for the transfer cross section, you need to have the mixing between the 2 cluster modes exactly correct. Otherwise, this is you're not going to reproduce experiment. And in fact, there is only one type of mixing that can completely reproduce experiment, and this can be done within the Noether shell model with continuum. So as an outlook, we can finally do clustering in like nuclei microscopically, take into account reactions, take into account multiple open thresholds. It's really, at least for me, exciting. So hopefully soon we will have extended everything to include the no-core shell model with continuum. So the core polarization effects that I mentioned were not included before, in some cases will then be included. And really, actually the beryllium isotopes offer a great opportunity for us to study clustering emergence from microscopic principles. So for that, thank you.
Thank you very much for this, this interesting talk. We have some time for questions. Yes, please. Dominique, I guess.
Yeah, Didier.
Didier, sorry.
Yes, I was wondering, so you compared the spectrum you got for the beryllium-12. Have you tried also to get the charge distribution of the ground state equally? Well, I discussed the experiment where we are supposed to be sensitive to the extension of the clustering of the ground state. So I was wondering, you compared your beryllium-12 just charge distribution, if you can.
I have not. This is very much related to something Guillaume and I have been talking about through emails about the workshop. Yes, computational, well, since it's a bound state, right, things are fine. You should be able to do this. We just don't have the, the actual code in place to do it. So it is doable. We just haven't done it. Or it should be doable, I should say, because there are always bugs waiting to be found.
Okay, Daniel had a question.
Thanks, Hans. Thanks, Kostas. I thought your argument about the impact of different clusterizations in beryllium-12 was really interesting. Can you show that figure again?
This one?
Yeah. So I want to understand the extent to which a clusterization that I would be really interested in seeing is already included in your calculation. So that is, let's call it beryllium-10 plus a dineutron.
Yeah, yes, it would be interesting. I completely agree. Actually, it is to me, it's the biggest negative in this calculation, right? Because the threshold opens around here. So it is definitely something that should be included when it comes down to making a full quantitative calculation and comparison with experiment. It's not as a dineutron per se, but just the two neutrons, right?
Yeah,
it doesn't have to be in the form of a dineutron.
Dineutron has scare quotes. Like I actually yeah.
Yes, I honestly do not have any feeling of how it will affect, because to me this 2+ was really a big surprise, for example, right? This increase in width was huge. My personal feeling is that including these types of clusterizations will have a significant effect in the no-core shell model RGM, because it will be closer to that molecular type orbital where it's alpha-alpha plus 4 neutrons. However, if you do it in the full NCSMC, where you include the core polarization, so you will have all the states and they will have no-core shell model type contributions. So this should be able to mask it.
Yeah, this is why I tried to ask the question carefully, right? Because so I also have, this is an extremely non-orthogonal basis, right? So understanding where different pieces of physics wind up is, it's difficult for me. My intuition sort of fails me in many cases here.
Well, me too, I should say.
Yeah.
It's very easy to get lost, and it's actually that's something that needs to be implemented. Is the relevant observable is the partial width in this case.
Yeah.
So it's looking at the resonances and extracting the partial width, and that will give you the information that you want. So
then, Hans, do I still have time to ask another question?
Yes, please go ahead.
So are you telling me that it would be interesting to make some sort of mapping to a R matrix? I know you guys have this sort of implicitly, right? But if I did like a mapping to phenomenological R matrix parameters, then that would be one way to answer these questions.
Yes, that's exactly what I'm saying.
Okay. Yeah.
Actually, yeah, this is it sort of boils down in if you want to do. Oops, sorry, that's the time I usually wake up. So the yeah, if you want to do a normal, if you want to do an evaluation, for example, of a cross section, right, where you have to get every resonance completely exactly where you want it, instead of just guesstimating whatever the resonances are in every, in this huge energy range, it is perhaps more instructive to do an ab initio calculation first. It doesn't have to be a perfect ab initio calculation, right? It has to just get roughly the same number of level densities. Then you can go on and do a phenomenological R matrix to do the evaluation completely.
I think this would be a great program. In particular, like if you had UQ for the ab initio calculation, you could then basically use the information to set priors before you do the R matrix fit.
Yep.
And so yeah, combining this with some sort of Bayesian R matrix tool could be extremely valuable.
Yeah, I completely agree. It's not something like that that is, new, right? New to me.
No, I think I think you're articulating it's a chain, right? And so the ingredients you need. Yeah, I think it would be great. Yeah.
The key ingredient is time, but that's a different discussion.
Time does you no good if you don't have good ideas, right?
Okay, so I think with this final word, we should go on to the final talk of this session, which will be by Wael El-Kamhawi, and he will give us a theoretical perspective on beta-delayed proton emission from beryllium-11.
Okay, thank you, Hans-Werner. Can you see my slides in full screen?
Yes.
Okay. Okay. So, yeah, first of all, I want to thank the organizers for inviting me to this interesting workshop. And in this last talk of this workshop, I'm going to talk about beta-delayed proton emission from beryllium-11 in effective field theory. So already on Monday, we had a nice talk by Yacid Ayad about this topic from the experimental side. And now I'm happy to present a theoretical analysis of this process. So this work was done in collaboration with Zichao Yang, Hans-Werner Hammer, and Lukas Platter. Here's the outline of my talk. So first of all, I want to motivate why it is interesting to study the decay of beryllium-11 into the continuum of beryllium-10, the proton, and the corresponding leptons here. And for as our theoretical approach, we use halo effective field theory for beta-delayed proton emission. So we already had some nice introductions and overviews, as well as applications of halo EFT, for example, yesterday by Daniel Phillips and Chloe Hepburn, or just recently by Sofia Quaglioni. And now I'm going to present halo EFT specifically for beta-delayed proton emission from beryllium-11. And therefore, I'll show you the effective Lagrangians in the strong sector as well as in the weak sector. And then I'll show our results of this analysis and finally end up with a conclusion. So why is it interesting to study the rare decay of beryllium-11 into the continuum of beryllium-10, the proton, and the leptons? So in 2011, the first cluster model calculations done by Bay and Tursunov calculated the branching ratio to be 3.010 to the minus 8. So this value is a really small branching ratio and therefore hard to measure in experiment. However, Riesager and company were able to measure the branching ratio in 2014 and measured a value of 8.3 10 to the minus 6. So we have a huge discrepancy between the cluster model calculation and the experiment from 2014. So a discrepancy given by more than 2 orders of magnitude. This led Riesager and company to suggest that there is maybe a new single particle resonance in boron 11, or Pfützner and Riesager also suggested that this is maybe a possible pathway to detect physics beyond the standard model. Now, in more recent experiments, as already shown by Yacid Ayad on Monday, in 2019, they remeasured the branching ratio to be 1.310 to the minus 5. So this is similar in size as the experiment by Riesager. But now, in contrast to the experiment by Riesager, they measured the final proton and really found new evidence for the resonance in boron 11. So this is a direct observation with a resonance energy given by 0.196 MeV and a width of 12 plus minus 5 keV. And the last experiment by Riesager and company, so they redid the experiment in 2020. They unfortunately found some inconsistencies between different measurements and therefore derived only an upper limit for this branching ratio by given by 2.2 10 to the minus 6. So this value is in tension, for example, with a value by Ayat and company, as well with their own value from the experiment in 2014. So this shows that the branching ratio for better delayed proton emission in beryllium-11 remains an unsolved problem. And now Halo EFT offers a new perspective on better delayed proton emission from beryllium-11. So as a reminder, and already mentioned many times in this workshop, the ground state of beryllium-11 is a halo state as depicted here on the right-hand side. So in the inner region, we find here this tightly bound core, beryllium-10 core, whereas in the outer region, you have this loosely bound valence neutron. The neutron separation energy is given by 500 keV, whereas the first excited state of this beryllium-10 core lies at 3,400 keV. So therefore, we have the separation of scales that we will exploit in order to describe beryllium-11 in Halo EFT, meaning we use the relevant degrees of freedom given by the tightly bound beryllium-10 core and the loosely bound valence neutron here. So now we want to investigate within Halo EFT this rare decay. So since the half-life of the single neutron is given by 10 minutes, which is much smaller than the half-life of the beryllium-10 core given by 1 million years, it is safe to assume within the halo picture that it's always the halo neutron that better decays in this process here. And in Halo EFT, the decay observables are parameterized in terms of few measurable parameters. And thanks to our EFT power counting, we can make predictions with a robust uncertainty estimate. And therefore, Halo EFT is well suited for the theoretical description of this decay and also provides robust uncertainty estimates. And with that, I want to show you the first, the strong effective Lagrangian we're using. So I depicted it here diagrammatically. So here we have the neutron propagator, the proton propagator. The dashed line is the beryllium-10 core propagator. And the second line, the thick double line, denotes the beryllium-11 two-body dimer. And the thin double line corresponds to the boron-11 dimer. And in the last line, we have the interaction vertices, allowing transitions here from beryllium-11 breaking up into the neutron and the core and vice versa, as well as boron-11 breaking up into the proton and the core, always in an S-wave interaction and vice versa. And here's the weak effective Lagrangian. So in blue, we have the leptonic current given here. And in red, we have the hadronic current that is divided into a one-body current and a two-body current. So on the right-hand side, you can see diagrammatically the one-body current. So here the neutron decays into the leptons and the proton, and the for the two-body current, we have beryllium-11 decaying directly into the leptons and boron-11. And the hadronic current themselves are decomposed into a Fermi transition, as well as a Gamow-Teller transition, where you have this Pauli spin matrix here. And these two-body currents here are showing up because we are working in the dimer formalism, and they enter only once we include the effective range at next to leading order with the energy-dependent interactions. So this is really a known two-body current and not a counterterm that is unknown. This unknown counterterm is suppressed. And now I want to show you the Feynman diagrams that contribute to this decay. So we have three diagrams here. Diagram A does not include final state interactions. So let me explain it. So we have here beryllium-11 that breaks up into the neutron and the core. The neutron then, via the one-body current, decays into the leptons and the proton. And these two charged particles, the proton and the core, interact via Coulomb photons, denoted here by this shaded ellipse. So this is basically the Coulomb-Green's function. And in diagram B and C, we take into account final state interactions. So the proton in diagram B and the core recombine into the boron 11 resonance and then splits up again into a proton and core. And diagram C is the next leading order diagram where we have this two-body current because of our dimer formalism, where beryllium 11 directly decays into the leptons and boron 11 that finally splits up into the proton and core into the continuum. And with that, I want to show you the results for the differential decay rate. So here's our result for the branching ratio if we do not include final state interactions. So this is basically taking into account only diagram A. Then we get a result of 1.31 10 to the minus 8. So similarly in size as the model calculation by Bay and Tursunov. And on the right-hand side, you find the corresponding plot. So here we have the differential decay rate as a function of the relative energy between the core and the proton. So our result is given here by the dashed dotted line, and the green band is our EFT uncertainty given by 40%. Whereas the solid line is the result by Bay and Tursunov. And as you can see, we have, once we do not include strong final state interactions, we have a qualitative agreement with Bay and Tursunov. However, these numbers are still far away from the experiment, which is why in the next step, we included or constructed an effective field theory that now includes a resonance up to next to leading order. And we use as the resonance energy the value determined by Ayat and company in their experiment in 2019, given by 0.196 MeV. And with that, we are able to calculate the branching ratio now in the new EFT, including the resonance up to next to leading order, to be 4.9 10 to the minus 6 with the corresponding experimental and theoretical uncertainties. So now including this resonance, we get the correct order. And on the right-hand side, you see the new results, including the resonance, as the dashed line here with a red band given, denoting the theoretical uncertainties. And so here are presented again the final results when we use the resonance energy given by Ayat and company, again the branching ratio. Moreover, we calculated the decay width to be 9 keV with the corresponding uncertainties. So this value is also in consistency with the experiment. They measured a width of 12 plus minus 5 keV. And we also calculated the corresponding log FT value to be 3.0 with beta strengths for a Gamow-Teller transition 2.88 and for a Fermi transition 0.96. If we would not include the Fermi transition, only consider the Gamow-Teller transition, we would get the same beta strengths of 2.88 here, but a log FT value of 3.1. And on the right-hand side, we did an analysis taking a look at the partial decay rate here as a function of the resonance energy. So let me explain the busy plot here. So the solid black line is our EFT prediction. If we vary the resonance energy, and the red band is our theoretical uncertainty given again by 40%. And then we have two green bands here. So the horizontal green band is the result from the experiment by Ayat for the partial decay rate, including the uncertainty. And the vertical green band is the resonance energy determined in the experiment by Ayat, including, again, the uncertainties. And the dash dotted blue line here indicates the upper bound by Riesager and company from their latest experiment in 2020. And if we compare our study to the experiment by Riesager, we can see that only resonance energies here greater than 214 keV would respect this upper bound. And comparing our results to the experiment by Ayat and company, we see that, so at 196 keV, we are here with our prediction, and now moving along this line, meaning varying the resonance energy in the uncertainty band of the experiment, we assign the experimental uncertainty. So this is why we end up with the experimental uncertainty here, basically moving along this line. And then on top of that, we add a 40% theoretical uncertainty, which is the value here. And as you can see, we have an overlap of our theoretical predictions with the experimental results by Ayat and company, and also this decay width is in consistency with the experiment. And with that, I'd like to conclude. So we saw that if we do not take into account final state interactions, that we get a qualitative agreement with Bay and Tursunov's cluster model calculation from 2011, but we're still far away from the experimental results, which is why we included then a low-lying resonance in boron 11 using the resonance energy by Ayat and company, and found that the partial decay rate as well as the resonance width is consistent with this experiment. And therefore, our model-independent calculation supports the experimental finding of this new low-lying resonance in boron 11. Moreover, we conclude that basically no exotic mechanism is needed to explain this huge branching ratio once we include the low-lying resonance. Okay. Thank you for your attention.
So thank you, Val. There is a question from Grigory.
I have a question about how you introduce this resonance. You have to assume certain structure because I think your result depends very much if it is single particle state or not. So how do you do that?
Can you repeat it? Sorry.
So the structure of this resonance will probably have a dramatic influence on your final outcome. So how you choose the structure of this resonance, because the width tells me that it should be L equals 0 single particle state. Is that what you introduce? How you do that?
Yeah, okay. So in this effective field theory, we include the resonance with up to next to leading order with two unknown parameters, the scattering length and the effective range, that can be calculated into a resonance position as well as a resonance width. And then we used as an input for our analysis the resonance energy from the experiment by Ayat and company. And that basically determines directly the scattering length. And what I did not mention is in our EFT power counting, we require that the better strength sum rule is fulfilled at each order within our power counting. And this requirement directly tells us the value of the second unknown parameter, the Coulomb effective range here. And knowing those two parameters gives us the resonance energy basically and the width. And as a so this is basically our result when we vary the resonance position. So if we do not require it to be exactly at 0.196, then you can see here how this partial decay rate varies when we vary the resonance energy while fulfilling always the better strength sum rule.
Did that answer the question?
Well, but you still, the structure of the core should have an influence, right? So,
yeah, this would be higher order contributions in our power counting that we did
make
not
the width smaller, right? So I'm just worrying that we're talking now about a very clean single particle state at relatively high excitation energy in boron 11. It may be there. I'm just surprised that it has not been observed recently.
Yeah, so compared to the threshold given by beryllium-10, the proton and the electron, this resonance lies at 196 keV, which is not a huge value, which justifies our treatment in this halo picture. But I totally agree that you at some point have to include core excitations, but that would, according to our power counting, enter at higher orders.
Yeah, when I said excitation energy, I meant excitation energy with respect to the ground state, of course.
Yes, yes. Okay.
Petra?
So maybe a little bit related question. So there are also 1/2 plus states which are bound with respect to the beryllium 10 plus proton. So is it possible in your formalism to cross-check your results and also calculate the transitions beta decays to do such a state?
To which state?
I mean, there's a 1/2 plus which is bound with respect to the beryllium 10 plus proton.
Once it is not too deeply bound, then it would be possible also to calculate it within this halo picture. Yes. So this is what I wanted to try to explain before, that it has to be close to the threshold given by beryllium 10, the proton and the electron. And everything close to that threshold would be possible to describe within this halo EFT. It's not with respect to the threshold of the ground state of boron 11. And if it's close, then it would be possible, yes, to cross-check it.
Okay, thanks.
Okay, I don't see any further questions. So maybe we can go over to the general discussion then of all talks of today's session. Are there any leftover questions from the audience that you would like to raise?
You mean for the second part of the session or for both?
For both. I mean, the discussion session is for both parts. Olivier?
Yeah, so I had a question to Belen, and it's probably also related to calculation to Rezus-Casal. And it's on the beryllium 14 2+ decay, for which Belen showed that it looks like a phase space decay. And I was wondering if the crosstalk conditions were checked very carefully, and if part of the low relative energy signal of the two neutrons is not cut by the crosstalk rejection conditions. So that was my question to Belen, and I didn't have time to raise it before.
Can I share my screen?
Yes.
Yes, please.
Yeah, maybe people will better understand what I'm saying. Thank you.
I think I have that somewhere. Yeah, so beryllium 14 is actually a very good benchmark for the crosstalk. And actually, this is how the spectrum looks like without the crosstalk. And when we apply the crosstalk filter, we actually end up with this nice narrow peak. So in this case, so we are sure that the crosstalk, we are rejecting most of the crosstalk, but the thing is that to be able to reject the neutron crosstalk, as you say, we could also eliminate some good neutron-neutron even. And this is more pronounced in the low energy part. I don't know if I have an efficiency curve here. So yes, so actually you can see this is the two neutron efficiency without the crosstalk filter here. And then the blue one is with the crosstalk filter. And you can see that this is more pronounced for the low energy region, which is the case for beryllium 14. So the fact that we see this cut at low energies for beryllium 14, I go here, that could come from the crosstalk rejection. But the thing is that the simulation for the three-body phase space is also taking into account the crosstalk rejection filter that we use. So I think we need a better neutron resolution able to really say something about this. But this could be the crosstalk, or this could come from the structure of beryllium 14.
Yeah, okay, and related to
May I just give a comment for this?
Oh yeah, yeah. Okay, please. Yeah.
Okay, actually, about this 2+ state of barium 14, actually Belen showed the older data from Riken, and actually we also looked at this correlation, and also we didn't see any correlation like Belen, so it was consistent. And at that time we also did this crosstalk condition cut. We used a different so-called different wall setup, so that I think we could actually reach rather good efficiency up to very low energies. So I think this is rather sure, I think, for barium 14 2+.
Yeah, okay, then it would be the one of the first case where, as you write, there's no final state interaction, which is a bit probably puzzling, because it would mean a very large distance of neutrons, or so maybe then I have a question to Jesus, because or to you. You showed, I think, some results about the neutron distance versus core neutron in beryllium 14 2+ from Jesus, but not the final projection of it. Maybe it's not yet ready. Maybe it's not done. Maybe.
Yeah.
Sorry. We are trying to explore also the beryllium 14 2+, but it's a bit more delicate, because I expect there the core excitations to play a role in the final distributions. Because if you remember, I said that for the 2+ in beryllium 16. This shape, this asymmetric shape in the relative energy distributions comes from the fact that you cannot have k = 0, this symmetric part in the hyperspherical harmonics. And the same would happen also for beryllium 14. But now, if you include core excitations, you can include more correlations and more components in the wave function. This could lead to a more symmetric shape in the distribution. That's something we still have to check, because so far the calculations don't include this effect. And I expect that combined with the fact that the energy is very low should lead to more symmetric shape like the one Belen showed, even if you have dineutron correlations in the initial state. So, but we have to see. That's just a guess.
Okay, very good.
Hopefully that will be the answer, but I'm not sure.
Yeah.
So, yeah.
Maybe I have a question also regarding this beryllium 14 decay to 2 neutrons. So you have this Monte Carlo simulation that did not include final state interaction, which agreed very well with the distribution that you measured. Do you also have a Monte Carlo simulation for the case when you include neutron-neutral final state interaction? Would that look markedly different?
You mean for beryllium 14?
Yes.
Yeah, actually, I do have that in my thesis, so I can just search the picture for you.
Good thesis.
Yeah. It probably depends on the distance of the 2 neutrons, and to get absolutely no correlation, it means that the distance of the 2 neutrons in this model should be very, very large.
Yeah, it's true that I think in the PhD there is such a picture.
Yeah, I'm just having problems to find it now. But actually, yeah, so what I saw is that you needed a very strong neutron-neutron interaction to be able to see something different from the 3-body phase space. So with just let's say, weak interaction between the 2 neutrons, everything really looked like the 3-body phase space. So we needed to go to the maximum of the neutron interaction we can get.
What is a weak neutron-neutron interaction for you?
Yeah, you cannot change it in principle, no?
Well, in this model, you can actually modify the distance between the 2 neutrons. So if you have the 2 neutrons very close together, you have a stronger neutron-neutron interaction. If your 2 neutrons are farther away, then the correlations you get are more like the phase space, because the neutron-neutron interaction is weaker in theory.
Oh, so the neutrons are out of range of the interaction. So the interaction is the same, but if you place them very far away from each other, then they are out of range and there is almost no effect. So this is something very hand-waving.
So if you think of that in momentum space, would that be the same as saying that the relative energy of the neutrons is so small that you're essentially they're non-interacting because the energy is below the energy scale that is set by the neutron-neutron scattering length?
This is how I see it when for these very low energy three-body states. Because
I'm not sure you can, I mean, Hans is valiantly trying to Fourier transform, and like it doesn't, you know, especially when you go down to p equals 0, you can't just say that that's the same as r equals infinity, right? So yeah, anyway, this is the figure, right?
Yes. So you see, we would see something already if we had like a distance between the two neutrons of 5 Fermis. So the distance for beryllium 16 was, for example, 6 and 4 Fermis. So that would be
that's an average distance.
That is the
it's some kind of average distance.
It's like some sort of RMS quantum mechanical thingy, right? Yeah.
Yeah, I think the two neutrons are in a Gaussian distribution.
Yeah. So I think that answering Olivier's first question, the green line would correspond to some final state interaction between the neutrons, and it should survive the crosstalk filter.
Yes.
So if there was such a signal in the data, we should have been able to see it. But the line that goes the best through the data is the phase space line. Almost. So the red line is almost phase space, unique.
Yeah. Also, the beryllium is a very except the fact that there can be halo, but in principle, it's a very small nucleus. So the radius is smaller than the fluorine that have been shown as well. So in principle, some signal should be seen if there is, or if they are very far apart, if it's very extended, or it's something that completely different than to this use of this simple model.
So may I add something to this?
Please.
Yes.
Sure. So we also did some calculations for oxygen 26. Let me show the screen. And actually, I think this is kind of a threshold effect, actually. So as you can see that when we got those energy correlations for oxygen 26 in different energy scales. So as the two neutron separation close to the threshold, actually the distribution becomes more close to the S wave, which will limit converge to a unitary limit. In this way, the asymptotic correlation section will become independent from the structures. So no matter what those decay energies is, the inner structures actually they have 3 different configurations. But when they go to the asymptotic correlations, because of the different asymptotic centrifugal barriers, if this decay energy is close through thresholds, this D wave will extend it to a very large distance and will suppress those D components in this systems. So only the S wave survives in the outer region. So that's why only the S wave can be observed in the experiments. That's what my understanding is for this.
But Simin, FSI would still be strong for you, right?
Sorry?
You would still get significant final state interactions in those S wave decays, right?
Yes, but for there is a S wave in the interactions between that, but since the decay energy is so close to the threshold, they only have S waves in this.
Yeah, yeah. But I think Hans is, well, I don't know if Hans can speak, but he's like here. I know I'm trying to map this onto our experience from helium-6, which is that even for very low energy neutron-neutron pairs, the FSI has a huge effect. In fact, we would say like it's super leading. It's more important than structure.
Yeah, I totally agree.
I think that the difference with respect to your helium-6 project is that you are only looking for small neutron-neutron energies. You don't care about the free body energy because you are knocking out the alpha particles.
It's true.
Quasi-free. Right. Here we have a very small free body energy already. So the total energy of the system in oxygen-26 is only 18 keV. So I think this goes more in the line of Hans. I think Hans' argument was saying that the energy scale of the three body system is much lower than the energy scale of the neutron-neutron interaction.
So Daniel, in our study of helium-6, if you would expand the FSI function in the relative energy of the neutrons, and this would be below 1/ma squared, then effectively this would look like a non-interacting system.
That's what you said before, and so now I hear that I should have realized this 18 keV number, right? So if that's the maximum total energy of the system, I get it. Right?
So it may be interesting to try to translate kind of our way of thinking about these things to this position space representation and see how that works together.
Yeah.
Well, one should remind that experimentally we see just momentum space. So you're always happy to plot this, and these plots are very beautiful with the distance of the neutrons and things like this, but we can never get this. And we have, unfortunately, the final result of a kind of a mechanism. We don't know if it preserves it as the initial wave function, or if it's finally dominated by the final state interaction, including transmission through barrier. So this is all the things that we have to make a bridge between your kind of calculation and our observables.
And I think, well, we didn't have time to discuss about Aldrich's presentation, but I think the interesting point in his presentation was, because obviously oxygen-26 is a stream case. Belen showed the beryllium-14 2+ that is quite low, but at some point this effect will disappear. We see again the effect of the neutron-neutron interaction. So I think what Aldrich showed, there are several cases that are at the border, a bit lower than beryllium-14, a bit higher than beryllium-14. I think the fluorine cases that you showed, Aldrich, fluorine-29, fluorine-28. So maybe by studying those cases, we can pin down this hindering or not of the neutron-neutron correlation signal.
He also showed in his talk not only the decay of the weakly bound, about the resonances just above threshold, but also to high energy state. And what was striking to us is that they look very much correlated. So despite, as he said, that despite there are a lot of states available for sequential decay, we were surprised that most of the events went into correlated pairs and ignore the possibility to go sequentially. Seems contrary to protons. In the proton, when it seems that when you have an available state in between, it goes to the intermediate state, and maybe it's due to the Coulomb barrier, because if you make sequentially, you reduce progressively the Coulomb barrier. It's less. It costs less than going through the barrier for the two protons. I don't know if you have any opinion about that.
Can I say something? I don't think that's the case in protons. I showed in oxygen 12, sorry, oxygen 12, the ground state, it has the intermediate state nitrogen 11 is quite accessible energetically, but the correlations you see don't reflect that. So in that case, it's very wide, the intermediate state. And one thing I guess I'm missing when you discuss that in the neutron side is how wide these intermediate states are. And maybe if they're very wide, you shouldn't really be talking about sequential decay.
So one thing about the Beryllium 16 2+ is that if you try to like plot these Dalitz plots, assuming a state at around 1.5 or 1.6 for Beryllium 15, actually there is not so much difference between the fragment neutron relative energy with respect to the three-body case. So in our case, we don't say this is a sequential decay because with just including the neutron-neutron interaction, the fragment neutron relative energy matches the simulation. But we could have some proportion of sequential decay to an intermediate state of Beryllium 15 that we cannot really see because it's kind of covered by the strong neutron-neutron signal we see. So that could be also a possibility. But just to describe the data, we don't need a sequential decay if we include the neutron-neutron interaction.
No, I think the remark of Bob was he was giving a kind of counterexample of what I was saying. Like to my knowledge, most of the cases where you have two proton decay, when they have an intermediate state available, they went through sequential decay. So he was pointing to the oxygen 12, and maybe if I understood correctly, you say that the intermediate state is very broad, so maybe it may look like direct while it's sequential or something like this. No, that's what you said, or
at some point, if the intermediate states come so wide, then the difference between sequential is immaterial.
Okay. And then you were saying in the case of neutron decays, you were asking if it's the same or if the intermediate resonances are narrow. That's what you asked, no?
Yes, that's what I was wondering, because a lot of these cases where you're wondering about sequential decay, there's no widths shown, so I was just wondering.
So in the example of the talk of Aldrich, I think he was showing a decay of fluorine 28. The width is pretty narrow because you see the two ridges corresponding to the sequential decay. But okay, we should give you a value of what means narrow.
I mean, if I may, it's kind of narrow compared to basically the energy difference between the initial state and the final state, basically. So if we look at the similar Dalitz plot as the one you showed for two proton emission, then we see clean lines because we have a good definition of the favored energy, which correspond to the energy of that intermediate resonance. It is true that in the case that I showed about carbon 18, where we populate very high excitation state, I mean, we don't know really, I think, the unbound spectroscopy of the carbon 17 in this case. So it's hard to tell what kind of state we should expect, but if they are narrow or not. But at least in, I didn't show it today, but in the paper, we also populated oxygen 20, which is isotone. In this case, we could see clean sequential decay through, so toward oxygen 18 plus 2 neutrons, but we could see signature of sequential decay in the Dalitz plots. So,
but doing more extensive analysis to this carbon 18 data, and we also see some sequential decay to intermediate states of carbon 17, and in fact there are recent results on that, and also older ones. And I don't remember the width of the states, but they are not so broad. But I can cross-check and tell you. But we see some decay by sequential decay, but the direct decay is by far dominant. It's like 85% direct decay. So it should tell us something about the correlations of the neutrons. So is that in the initial nucleus, and the deeply bound, the knockout from deeply bound state is so sudden that they preserve this correlation, or is it something totally different? That's the question. But we were surprised to have such kind of big amount of direct decay fraction.
Daniel?
Can I change the subject?
Please go ahead.
Yeah, please.
So I have a question for Nakamura-san. So, and I don't know if Caitlin Cook is also here or not, so I haven't looked on page 2. But so you have now done many experiments where you've done Coulomb dissociation of 2 neutron halos. The data are really nice. And I was very struck by the fact that you were emphasizing that the BE1, the total BE1 strength in boron 19 was close to that for lithium 11, right? So I wondered what you think of the idea that this, let's say dBE1 by dE curve is somehow universal across all 2 neutron halos.
I don't think so. Actually, the shape is different.
Well, the shape depends on, I mean, as you emphasized, right? The shape, from the shape you get information on the binding, on the S2N, right? So you need to do a little bit of, you need to plot it versus, I would say, the ratio of the outgoing energy divided by S2N. And then there is some dependence on the mass factor.
And also the configuration affects, I think, the if it's S wave dominant or P wave dominant. For instance, it's very different between lithium 11 and helium 6, for instance.
Helium 6, I agree, right? But for these nuclei that have a significant S wave component, they also have in common. This is sort of related.
I remember, for instance, for the case of lithium 11, actually, it was affected by the spectrum of lithium 10 final state.
Yeah, so, you know, Matthias Goebel and Hans Venner and I, sorry, go ahead, please.
Yeah, so I think, well, I didn't, so it is affected also by the scattering lengths, for instance, between boron 18 neutrons. So yeah, so there are several ingredients to determine the shape. So it's not universal, I think.
So I guess the universality would be, I can think of a couple of limits I could take where these would all be related. So one limit that's very interesting from a theoretical perspective is where all the two-body scattering lengths go to infinity. So then that limit, there's only one. So you're actually not, you know, at least it seems to me, not that far away from that in boron 19. If we take the boron 18 number as gospel, right? So then the only scale left in the problem, right, assuming for the moment pure S waves, is the three-body binding energy. And so it's sort of a theorem that in that case, for a given mass ratio, or, you know, once you adjust for mass ratio, then everything is, you know, the same curve, right? The technical statement will be that the curve is a function only of E over S2n and the mass ratio.
Yeah, if that's the case, it's interesting. Maybe, yeah.
Yeah, I mean, so this, to some extent, this is
try the calculation.
Yeah, that's right. I was going to say, to some extent, this is our job, right? Is to try these things and see how well they work. And I mean, I understand that there are other configurations present. So this is in the EFT spirit. This is sort of this would be true at leading order, and then there would be corrections which are structure dependent and these other things that you mentioned. But even if this was just a leading order picture, I think that would be really interesting because it also connects it to things that people can measure in cold atomic gases.
Yeah. Okay. Interesting point. Yes.
Yeah.
Thank you.
Olivier, please go ahead.
Yeah, I had a similar. I had a question also related to the BOV1. So it's good that I'm following the previous question, and so my question is the following. I was surprised that you could extract so many information from a kind of integral value, or I mean, kind of B1. So I would like to ask you if it's if you don't have several solutions that would finally give the same curve, and just to finish, and if so, which kind of experiment would you advise to do complementary to this one to better constrain what is not so what is uncertain?
Okay. First, big uncertainty is actually the 2-neutron separation energy. So if we are sure about this 2-neutron separation energy of 0.5 MeV, that would be already very nice. And so I want someone to measure mass directly with high resolution. That's one thing. Yeah.
Well, in fact, it's not as difficult as it seems for unbound nuclei, because you can get kind of easily the 1-neutron separation energy by having the energy of the unbound state. So you have the SN quite easily, and even at 50 keV resolution beyond replying. It was shown by Belen that in boron up to boron 21, she could get the systematics of SN oscillations. So very
yeah. Okay, so the unbound state is maybe even easier for us.
Yeah,
because we can measure relative energies. But the bound states, we need to measure directly the separation energies. And yeah, that is a bit, I feel, you know, behind. I mean, and the other thing is that we have still a problem of this shortage of calcium-48. That's, yeah. So yeah, anyway. And of course, the other question you raised is of course, we also think that maybe other theories can reproduce with different configuration as what was the name?
It was me, I think, this morning.
Yes, you. Jesus Casal-san. Casal-san. Yeah, you said that actually the different configuration can reproduce our data, right? So there are some other uncertainties like the S-wave component. Yeah, scattering lengths can be extracted in different way. Actually, Miguel has this data for a long time, so I think you should publish this.
Yeah, yeah, we should.
Yeah, as well as the boron 18 spectrum. Yeah. So in different approach, we can probably converge.
So are there any other points that should be discussed? Miguel, do you have something?
Yeah, well, maybe taking advantage of Nakamura-san's being here, even if it's very late in Japan. So do you have any comment on the fact that both oxygen 27 and 28 are so narrow?
That is, yeah, that is actually.
Well, in fact,
I don't know why. Actually, I don't know why.
Oxygen
But
26.
I feel really actually I feel lucky.
Yeah, because oxygen 26 is also very narrow. So
because if they were not narrow, you haven't seen it. Probably.
Yeah. So this was kind of lucky, and I would like to know how theoreticians think why this is narrow. Any idea? Well, the other thing is, yeah, there are many questions now, actually.
I don't understand the question, Takashi, because
so you know that the oxygen 28 is already 4 neutrons away from the stability. So even so, oxygen 28 shows rather narrow resonance. So why do you think it is?
Well, if the separation energy, 2 neutron separation energy is so small, as you showed, right, then it must be narrow.
It must be narrow.
It's just Q value argument, right?
Is it? Yeah, but not always, no? Sometimes we see some like, I remember the case of, for instance, helium-10 or helium-9. Those are rather broad, I remember, I think.
Or lithium-13, I think that the spectrum that Aldrich showed on lithium-13 is quite low energy, but it's not so narrow. So oxygen 27 and 28 are narrower than the experimental resolution.
Yeah. So is it? I thought that is kind of accidental. There should be some interesting mechanism there. Well, one thing is that it's in the D3 half region. So, but there is always a mixture of other configurations. So I don't know. Yeah. Of course, helium and lithium cases, maybe S-wave contribute to make it broader, I think.
Well, probably it's the structure of the state as well, because if you look at there were data from fluorine 15 on the proton rich side, and by Valerian Alcindor, he was showing that this nucleus is unbound in the ground state. So he was showing that the ground state resonance was about 200 keV, and the one above was a bit even larger. And then there was a state like few tens of keV at about 5 MeV, 6 MeV excitation energy. So the states were very narrow. So it's not because they got very few energy available, because they got a lot of energy available. it's because we suspect that they have some clustered configuration. So the overlap between the one proton decay for this state is very small, and they should rather decay by 2 protons, but they don't because of their low energy. And similar thing, it can be said for fluorine 28, which is also unbound in the ground state, for which there's a narrow resonance, 2 neutron. We suspect 2 neutron resonance above threshold. So again, it could decay and be extremely broad by 1 neutron decay, but it's narrow, probably because it prefers to decay by 2 neutron decay. And in that case, it does, because there's no Coulomb barrier to avoid it to decay by 2 neutron decay, contrary to proton decay that is harder.
Isn't what Vitek, isn't what he really was thinking is that it's very close to the threshold, so there's no phase space, and the structure is a dead ringer for that decay channel, and therefore spectroscopic strength in any other decay is essentially 0, and therefore it has to be have a small width.
Yeah, but would then that be a meaning for some meaning for the oxygen 28 4n? Like it has some more 4n than it dependent 1n, something like this. So something we should question, but Vitek is right. Altogether, the total energy available for the 4 neutrons is not very big there.
And also
we did not, of course, have chance to analyze carefully the data which Nagamura-san showed us today. It was just one slide, which I understand is still secret, right? But it, everything depends now on how narrow is this peak in oxygen 28. If you read this paper by Kevin, okay, Fossett, which you referred to in your presentation, there's some discussion about this, 2 times dineutron system, right, in oxygen 28.
Mm-hmm.
Okay. I think it's quite fascinating question whether oxygen 28 will go to oxygen 26 and then will go to oxygen 24, or whether there will be some small 4n branch. I mean, this opens up, extremely interesting area now.
Mm-hmm.
If you are really convinced that this little narrow peak which you see in oxygen 28 is reality.
Yeah, we believe that. Yeah, now I think we can publish this hopefully soon. We have draft already, but we have still discussions, and we are working on this.
So we are all very intrigued and would like to see it in press, right?
Yeah. We are working on this. So yeah, and hope we can discuss more after publication. Yes.
It should be published before the next real Trento workshop in Trento.
Yeah, sure.
Well, there will be this meeting at MSU next week, right? On neutron decays, right? And outside the drip lines.
Yeah, but it may not be published at that time.
No. But this will be the next opportunity to meet and talk about it, right?
Neutron decay. See, I don't know that meeting, but.
So, Belen, could you send Takashi information? Oh, it's already in the chat.
Okay.
But this is the meeting where Saito is going to present her work.
Okay. Saito-san is invited. I see.
Mm-hmm.
So if I understood well from the talks of Simin and Jesus, you were both saying that there's a modification of the, or how do we say, apparent wave function, and the flux will go mostly in the S wave whenever possible. That's what you were saying. Is it correctly summarized or not?
Yes, well, when it decays through internally through the barriers, it tends to transition from the high L orbitals to low L orbitals. Yes.
But it can be driven by p orbital, or it's always S, or
it depends if the angular momentum make that S wave impossible. It can only change it to P waves. But if S wave is possible, I would say it always favor the S wave because of the lower centrifugal barrier.
And wouldn't it also be true that if the energy is low, this effect becomes even stronger?
Yes, yes.
Yeah.
And so the S wave dominance for these near threshold resonances in the neutron side have got to be heavily S wave. I mean that.
Yes. So this is this old argument by Wigner, right? Which I presented in the beginning of the meeting. You know, S wave gives always rise to very large enhancements. And this is the same argument as the argument for neutron halos, right? So that's it, right?
Yeah, but for neutron halo, it works as also for P waves, no?
But P wave also gives rise to a kink and divergence, but it is much weaker than S wave. You are right. P and S waves will always win.
But for the fluorine isotope, we have seen that with the collapse of n equal 20, and the emergence of intruder configuration, the P wave is there. So, but the S is a bit far in this region. This is why I was asking if you expect to still have a S wave dominance or not.
I would, so Olivier, I would not use shell model arguments for such systems. You know, you have all this S wave continuum around you, okay? And you can get this component, not that difficult. So again, you know,
yeah,
shell
even
model arguments, be careful here.
Okay, but that's an important point, because you seem to mean that the structure is not very essential then.
Yes.
No.
I would say
so. You would say a very tiny component of S is enough.
Very tiny component of S wave is enough, and we learned this from this ancient, you know, spectroscopic studies of 1 proton emitters. Okay, heavier proton emitters. If there is little possibility to get a flux in S wave, the system, the width will be totally determined by this little component.
Yeah, but for the proton, there's the Coulomb barrier. For neutron, there's centrifugal barrier.
So it's even better, right?
Yeah.
Right.
So I don't know if there are other things that someone wants to discuss, or if the organizers want to, because we will not meet tomorrow again. This is the last session.
This is our last chance to, if you have questions, this is your last chance.
Or maybe the organizers want to say something.
Guillaume may say something, or I, or
we should thank all the speakers, because it was a very nice workshop.
Yes.
And also the conveners. And to remind you that hopefully there will be the opportunity to be in person next year. Because, it's better for discussion and a new collaboration to share some drinks than to be in front of a computer.
Yeah.
watching TV. You know.
Lucas, you want to say something?
Me?
Yeah.
I just want to thank everybody too. And I think, so I actually just want to remark, so I find these video meetings have something very intimate because you only see one person at a time and usually everyone mutes himself or herself. So then the remainder of the group is very crowded. We also didn't have any cell phones. That seems to happen in Trento all the time, that someone forgets to turn off the cell phone and then has to storm out of the lecture hall. So yeah. So there were some good things about this too. That's what I wanted to say. So even despite the fact that we had to stare at the screens, but I really enjoyed this a lot. It was fantastic. Thanks everyone.
Yeah, so I can say a few words as well. First, Alexandra is apologizing because she's attending the Ganil PAC today. So she's doing a very important job for our future. So she could not, unfortunately, attend this day. So I appreciated also very much the work of the convener. You went beyond our expectation by chairing this session and steering discussions. I like very much all the talks, and also especially the synergies between theory and experiment. This was really great. This equilibrium, the balance is not very usually easy to do, but it was really great because also theoreticians didn't go too much into the details of the equation. So that was really great, and I hope that we can continue this in presence, as it was said.